In this example, we're going to be talking about an ideal vapor compression refrigeration cycle. So this refrigeration cycle uses uses R134A as the working fluid and operates on an ideal compression cycle between 0.14 and zero point 0.8 megapascals. The mass flow rate is 0.05 kilograms per second, and we want to determine the rate of heat removal from the refrigerated space and the power input to the compressor, the rate of heat rejection to the environment, and the COP of the refrigerator. So in this case, we have an isentropic compression process. Right here, we have put work into the system. Right here, we take heat out of the system through the condenser. Right here, isobaric condensation process. We come through our expansion valve right here. This is a constant enthalpy process. And then we extract heat from the refrigerated space with the evaporator right here. So what we're going to assume is that this cycle is operating in steady state. Kinetic and potential energies are zero. We want to find the heat entering the system, the heat leaving the system, the compressor work, and the COP. So we have most of the information we need. We can just go ahead and write our state points. So for an ideal cycle, we can assume that refrigerant is entering the compressor at a saturated vapor state. So it's got a quality of exactly 1 right here. Right here, as it comes out of the condenser, we can also assume that it comes out of the condenser at a quality of 0. So we can go ahead and determine those things. To help us find 0.4 right here, we know that if we do a first law analysis on our expansion valve, we're going to have a constant enthalpy process across that expansion valve. So then we can just determine the enthalpy of those states. So to find the heat rejected, or the heat that is coming in from the low side, which is on the evaporator side, we have a known mass flow rate, we have known enthalpies. We can go ahead and find that. We can go ahead and perform that calculation, 7.2 kilowatts. Same thing for the compressor. We can go ahead and do a first law analysis on the compressor. Mass flow rate times the entering and exiting enthalpy. And that gives us the power required to operate this ideal process. For part B, we want to find out how much heat we're rejecting to the environment. Again, we can do a first law analysis. Mass flow rate times delta H gives us 9 kilowatts. What we could also have done is determined because we know heat is entering the system on the low side and we know that we're putting work in through the compressor, that must equal whatever we're rejecting to the environment right there. So 7.2 plus 1.8 equals 9. For part C, we want to find the coefficient of performance. So that's going to be effective or useful, the useful part of the heat transfer over the work. In this case, we're interested in the low side since it's a refrigeration cycle. If it's a heat pump, we're going to be interested in the hot side, the condensation side. But in this case, we're interested in how much heat we can extract from the refrigerated space. So that comes in from the evaporator on the Q low. So 7.2 divided by 1.8 gives us a COP of 4, which signifies to us that for every 4 units of thermal energy we get 4 units of thermal energy removed for every 1 unit of electricity energy we put into the system. Compare that to, so say if this was a heat pump, if we compared that to a straight up electrical resistance heater, that would have a COP of 1 unit of electrical energy for every unit of thermal energy. So if we went back up here and we took a look at this and said, we're just throttling this process right through from the condenser to the evaporator. This is just going through a throttling process, so we're losing a lot of energy we're just throwing the energy away, dropping the pressure to get it down to the lower pressure. If we were able to put an isentropic turbine or some sort of two-phase expander on that, what would happen? Well, the turbine would produce about 0.33 kilowatts, which would decrease the power output to the compressor. The power input to the compressor. So that would decrease our power requirements. It would also increase the refrigeration capacity from 7.2 to 7.5 kilowatts. So the result would be a COP of 5, which would be a 25% increase in performance. That's not done practically because we're going from a saturated liquid into a vapor expansion. So this is a two-phase expansion process, which is not practical in real applications.